by the way, my name is Mike Underhill, it's down there somewhere, and it's my job to, as chair of the events, IET Sussex events committee, to put these things on. Right, the next thing to do is to introduce our speaker, which is Dr. Tim Brown, who's Senior Lecturer in RF Antennas and Propagation at the University of Surrey. Well, I've been at the University of Surrey for a while, and I've seen Tim rather for a number of years. Let me tell you that the first real thing I did with Tim was to actually examine his PhD, which was on antennas. In 2002, he was a student, and I think you were an undergraduate as well, an undergraduate and then a PhD student, but that was in 2002. And as I recall, well, it was a very interesting, actually, a talk that he gave for us. So he did pass that. Anyway, the next thing that Tim did, he hot-footed over to Denmark from 2004 to 2007 and worked in Denmark. What was it, Tim?
Aalborg University. Aalborg, it's not.
Okay.
Or Aalborg, as the English call it, yes.
So he worked there, and then he came back to Surrey in 2008, and so 2007, I beg your pardon, it was 2007, beg your pardon. And then I got to know Tim again, because although I had at that time left the University of Surrey, I was still doing some lecturing for them, which we both are doing today. Continue to do various courses, antennas and propagation and microwaves and things like that. We're doing various courses which we have in common. So I see Tim regularly 2, 3, occasionally 4 times a year. So anyway, that's very nice. And so I can assure you that he is a real expert in this very interesting subject. And so really, what else can I say? Over to you, Tim, please.
Thank you very much. Well, I think we'll have to just do the little changeover we need to do here, which hopefully will do what it did last time. Oh, yes. Oh, well done. Great. Yeah, well, thanks very much for the invitation. It's been quite interesting to come to an IET event on the other side of the stage, as it were, because actually another interesting thing is I'm also a well-known IETite, probably a notorious one, in that I am the events chair for the IET Surrey local network. So I'm normally doing all of the things you're doing, running an event, inviting a speaker along, and indeed I am also editor-in-chief of the Microwaves, Antennas and Propagation Journal of IET as well, so have been involved in quite a lot of activities that they do, and it's been interesting to come and see the local network, see how you operate similar to us. I'm glad that we're not doing too posh things when we do catering, because we thought having China hire for having decent cups of tea and coffee was too posh and too much for what IET would expect, but I'm glad to see that another local network thinks it's a better thing to do as well. So, minding the peripheral things, we'll get on to the technical content, which I need to take responsibility for as an engineer. And I should also give credit as well to good friend and colleague, a visiting professor now at Surrey, Professor Ben Allen, who was formerly a Royal Society Industry Fellow when he was working for Network Rail back then, and he's now moved out of that sector and working for OneWeb, but back then he was working on this idea of, or this concept that had become a bit more prevalent in the RF world, known as orbital angular momentum, where there was a lot of skepticism from it from engineers like myself and others who do engineering with multiple antennas effectively, and it is a multiple antenna application. But I went along to him and I said, well, I've got this idea for trains where you could unravel this and make it into what I would call linear angular momentum. And he said, yeah, I get that. And actually that was at an IET event as well, these sort of day events they do for antenna and RF engineers at Savoy Place. So IET is a good place for conversations and networking. And I said, this could really work, and he liked that idea. And so I got experimenting, got a student to do a project with me to get through some experiments with it, get some preliminary results out. We got the seminal paper out into the Royal Society proceedings, which was very nice, and because he was a co-author and a fellow, that meant I didn't have to pay the publication charges, similar to the extortionate amounts IET now charge as well for their publications, but that's an aside. So that's been a great encouragement to get that through and actually get this beginning, and we've just been now finding every opportunity we can to take the work further, and really where we've seen it go is that the potential solution this has for solving the problem of connecting our trains to the internet and to 4G, maybe 5G services, which of course still to this day is anything but decent. As indeed I tested on the train on the way to see if the Wi-Fi was working any better. Couldn't even do a speed test on it, so I don't have a lot of faith in it right now. But it really, we saw that this concept was going to be the answer when it came to tunnels. I mean, a lot of the problem actually with why trains are not connected is largely economy, and it's who pays for it. Is it the train operator or the network rail or the customer? And indeed that's that can put up the price of the ticket, which is already high enough. So you could put masts alongside the train track, connect them with fibre or wireless links, fixed links to get the connectivity, but it does just cost, and it's heavy. And obviously we need to be looking at newer low-cost ways, energy-efficient ways to make it possible. And I think those are coming along, and hopefully more investment will get into our rail infrastructure to make this a priority, because we have all this hype of many Gs along the way, but actually it doesn't really to me matter what G it is. My research has always been interested in how do we sort out the coverage problem, regardless of what G that is, and of course that can relate to, satellite communications for global connectivity, which is another thing to solve. As well as innovative, cost-effective ways that we can do rural reach on a terrestrial level as well. And that's largely inhibited by economy, but we are still looking at ways that could be improved. But rail comms gets very interesting, and so what I will do is really talk about what this orbital angular momentum was. Something very controversial at its time when it really came about for a radio in around 2012, 2011. It's been heavily used in optical communications, and it's very good for optical. And so actually I think it was kind of nice in a way that it was a bad idea, and still people did a load of research on it, because actually it helped me to think out of the box eventually and think, well, why don't we turn this into something that's good for RF but not good for optical? And that, I think, bore that idea, and that's a really great thing. So, all being well, if we can get it to technology readiness level 3 in the coming years, it might go somewhere. We will see. And I'll tell more about that story later. Let's try the next slide. Now, I wanted to check, yes, how many in the audience would you classify yourself as either past or present engineers or physical scientists? Most of you are. Yes, I think nearly all of you. Hopefully that means that all of you would understand what the term phase shift means, because I wanted to make sure we got that right. And I think if we didn't understand what phase shift was, it would be very difficult to make any sense of orbital angular momentum or linear angular momentum. And so that probably means I don't need to spend too much time on the other slides, like the first few slides I've got, which are more the kind of slides probably that would get used in lectures in this very college, because it's a sort of post-16 education type thing, where of course we can have a sine wave coming from a source, and of course we could offset that source to and create a phase delay, and we shift the wave, of course, so we do get a phase shift. But those who do know what phase shift is, one thing to take note of is that I'm going to talk about phase shift in terms of length of lines. So, of course, because of where the solid wave is positioned, we've got a long solid line, and then we've got a slightly shorter one relative to the source to tell us that that has a certain phase shift. So in the some of the next illustrations I'm going to use, I'm going to be taking arrows like that of different colours so we can appreciate what the phase is at a certain point. And that will help us conceptualise it a bit better. So what is this thing, orbital angular momentum? And I'll get to a point where we discuss what the momentum is. I was consciously thinking when I was preparing this lecture yesterday, somebody might ask me, what is the momentum? Where is the momentum? Because I haven't, as an engineer, you know, we talk about how it works, not why it works, isn't it? The scientists talk about why it works, and for the scientist, defining the momentum and what that actually means and why is it orbital and angular, why do we conceptualize it this way? But to start with a straightforward illustration, taking these analogies of phase shift, is that we could have a ring, and we'll take this dotted line to be a direction of propagation of the radio, or indeed the optical light, it could be. And let's say at the top of the ring, at that point, we have the starting phase shift. It could be 0 degrees or whatever. And as we start to go around the ring, gradually, we start to shorten the line. So we start to adjust the phase as we go around the circle. And I'm going to have to do this slowly with this, but that's a good thing, because it's probably going to slow me down, so you will make sense of it. And because I have presented this at Amateur Radio Society lectures as well, and they found it a bit fast for some of them. So as we keep going around the circle, the phase gradually changes, and in this case, actually, when we get to the bottom of the circle, the phase has changed so much that actually it will have shifted a whole 180 degrees by the time it gets here. And we keep going around the circle and shift the phase even further. Because as we all know, you can shift a phase really anything between 0 and 360 degrees. So we can keep going around to the end of the circle, and indeed our phase shift, when we get to this point at the end, and of course we're just changing colours here for clarity, we can say that we've got to 360 degrees by the time we get to the top of the circle. And of course that's the same as 0 degrees. So what we've got is a source where we are adjusting the phase as we go around it. And I need to come to a point here, yes, about the idea that we're essentially, yes, playing a tune. And we'll find in a moment you can get different modes of orbital angular momentum, where you can play different tunes, essentially, and you get different colours coming out. But I think the interesting point here is, yes, where's the momentum? Because, of course, in physics terms, when we learn about momentum here at college or something like that, we would be obviously told about the mass times velocity, and how when something hits something, momentum is conserved, isn't it? And it determines the velocity it goes on at. And of course we can also take that to things we learned about circular motion, where you would have a centripetal force, a centrifugal force, and the sort of couple that it needed to make the circular motion work. And when we look at things like the gyroscope, or indeed I've seen other lectures on YouTube where they get the bicycle wheel, don't they, and they turn it very fast and hang it off a rope, and then it just stays vertical, doesn't it? Of course, orbital angular momentum is very crucial to many functions of the wheel and anything that rotates. Of course, what we see there is a rotational momentum, don't we, in a sense. Obviously, there is quantities of mass around the edge of that wheel that are turning with the velocity as it goes around. So it keeps going and is sustained. Obviously, a physicist would explain all of that far better than I do as an engineer. But of course, we haven't got, in electromagnetics, we haven't got something physically moving as such. What we've got is, yes, I'm looking ahead at this ring and I see a change in phase, but you could look at that like, okay, if I take each of those sources and I'm moving towards the source or away from it, obviously each of those phases, as I displace myself, will change. And they'll all change with each other. And so it's a bit like, yes, I start here, I see that set of phases, I could move a bit closer and I would see then a different set of phases. The 0 degrees wouldn't be up there, it would be somewhere around there. So that could be, as I move in and out, it's a little bit like the source has turned around physically. But obviously everything's happening electrically. And that's how I would see the best way to visualize the momentum. And of course it is orbitally changing around that circle, and we have got a motion in a sense in that way. And of course you could also be actually standing there as well at a fixed point, and then you could think of this as just a load of oscillating waves that are all obviously changing in time as well. And so yes, as I'm standing there, it's travelling. Obviously, the amplitudes are changing, all of them, and it would feel like something if you could feel the electromagnetism. Not that you would, but it's like that's turning around. There is a momentum there. So that's the best illustration I could give. And also another thing that when you do read about OAM, they also talk a little bit about spin momentum, which I don't really need to get into per se, but that's where in each of the sources you could alter the polarization, because usually any electric field or even magnetic field will have an orientation, a polarization. It may just be vertical or horizontal, or indeed it could be what we call circular polarization, where it's effectively spinning. I won't go into the details of how you make circular polarization work. If you want to know about that, yes, you can indeed come along on the antennas and propagation course that me and Mike teach on, and we will teach you everything there is to know about that. And so we don't want to give away the trade secrets here. And obviously that can happen together with the orbital angular momentum, and it's important that those two things are distinguished from a theoretical perspective. But we can just not need to really worry about the polarization. It's just these are our sources. So that's kind of what we understand that to mean. Now the other thing with OAM is, and the whole point of OAM, is that you want to be able to transmit many modes, so that down an optical fiber cable you don't just have to send one source of light. You could send more sources of light, each one having their own mode, and they could all multiplex down that fibre and not interfere with each other. That's the purpose of it. Because if you didn't have them in different modes, they would all just superimpose and overlap each other. They wouldn't be decodable at the other end or demultiplexable. And so there are many modes you could make. But for illustration, I'm going to compare mode 1 or mode 0. Oh, actually, no, it will be mode 1, sorry. Compare that with mode 2. Because with mode 1, you may remember, we went from 0 all the way around to 360. And so with mode 2, what we can choose to do is instead go from 0 to 360 degrees phase by the time we get down here. And then you would start again from 0 to 360 going that way. So what we have, the difference that we have is essentially a phase gradient, or the rate of change of phase. So if we gradually go through it this time, we'll find that the lines are getting shorter and they're changing colour a little bit more rapidly, or twice as rapidly, you could say. So they getting all the way to the red point where they get to 360. And so we can go back to 0 again. And we can go around the rest of it and go and go from 0 to 360. And we should find we eventually end back at 360, so indeed that will of course join up again with the 0 degrees. And so we can start to understand from this really how you would get more the third mode, because the third mode would just have a rate of change 3 times the first mode. So if we were to work that out in our heads, I think by the time you got 120 degrees around the direction of propagation, you would have done 360 degrees. For the next 120 degrees, you do another 0 to 360. And then for the final 120 degrees, you do 0 to 360. And that would be mode number 3. And yes, you could go to mode number 4, mode number 5, if you've got enough sources. And indeed with optics, they have the capability of making quite a number of modes. I'm not quite sure how many they do in practice, so I've not looked it up for optics, but that tells us what really enables us to multiplex these. And indeed, when you receive each of these modes, you need something at the end that obviously will respond to one mode by having phased offsets that it needs to get mode 1 and then mode 2 and whatever, and then if you're transmitting mode 2, mode 1 will not receive it because when the phases or conjugate phases, as we know in maths, go on top of each other, they're effectively orthogonal, so they don't interfere with each other. You try and put mode 2 to receive mode 2 with mode 1, you will get nothing. Although of course there may be imperfections and impairments in the system, which means that mode 2 might leak a bit to mode 1 and you get an inter-mode interference. And obviously how we design things to avoid that is quite important. So hopefully in all of that, going through it carefully, I have been able to explain the difference between 2 modes. We can appreciate what the momentum actually is, and knowing phase shift. Yes, in theory, there are an infinite number of modes. We could just have an infinite set of sources there, or a set of sources that have got enough resolution, and then yes, you would, if you want to go to an infinite number of roads, you would have to divide your circle up into an infinite number of sectors, keep them going from 0 to 360 in each sector. Obviously, there will be a practical limit. And in theory, yes, OAM has been sold as, oh, you could, the sky is the limit, you could keep going. And with optics, they probably got quite a long way. And then some physicists came along and said, why don't we do this for radio? Yeah, we could just keep doing the same thing and go and make all these modes and reach unbelievable number of modes and transmit data down each of those modes, and we could transmit so much more data over wireless than we ever could. And this reached an awful lot of skepticism in the RF and communications, wireless communications community, saying it's just nonsense, it's not possible. There's always physical limits on everything, and we know Shannon theory, which basically tells us what bandwidth you've got and what signal-to-noise ratio you've got at your receiver. It will tell you what maximum transmission you can make, and you can't just go magically making lots of different modes to transmit over the airspace. It doesn't work.
How many modes can you make?
With RF, well, I think the number I've seen is getting around 6, but even then it's still hard to decode them. Yes, so we'll see when we do it with RF and use antennas how that will look. To just show how these physicists in Italy did it at the time, and actually they were amateur radioists as well, so because a lot of these things in radio seem to start life in the amateur community, or the amateurs get involved, and that helps the professionals work out what to do with it. Yes, this was in 2011, and indeed it was published in a physics journal. It's quite well known, and they did the first antenna that could deliver an OAM mode over wireless, and they used a parabolic dish reflector antenna, which of course are used a lot for satellite television receivers. And what they did was they cut a slit in the parabolic dish, and of course started to make it a little bit into a kind of spiral. So of course all the reflections that are coming from the source, and the curvature on these parabolic reflectors is designed such that everything will reflect out in the same direction. Obviously they could get that mode to essentially transmit as it needed to. I mean, this particular measurement wasn't anything particularly amazing, because what they were wanting to prove really at first was that actually it was an OAM transmission, not that it was actually doing any of this multiplexing as such. Because it's worth popping back to the previous slide just to appreciate this. Taking mode 1, if you take this 0 degrees source and then directly opposite it at the bottom, we said that it was 180 degrees down here. And actually you could take every pair of those and keep going around. So you're actually transmitting something where on the other side, opposite side, there's something out of phase with it or in anti-phase with it. And it doesn't matter what angle you are around that circle, there's always going to be something in anti-phase with it. And that's the same for mode 2. Well, not diagonally opposite, but it would mean in this case you've got 0 degrees, 180 degrees there. So yes, it would be like that, isn't it? Wherever you go around, you've always got a counter anti-phase for every phase you've got. And of course, if you add fields together that are out of phase with each other, we know what we get, don't we? We get nothing. So the bizarre thing about these OAM antennas, when they're used in RF, is that, yeah, if you were to look directly ahead at it, you wouldn't pick anything up. And it only means that when you start looking at it from an angle, those antiphases don't quite happen. They're maybe almost an antiphase, but they do start transmitting outwards, and the further you go, the further apart they get. And so what they were doing here was they were having to put 2 of these Udayagi antennas, like television antennas, to spread them out and see that they could still pick them up at those 2 far angles. And that's what it proved. So, of course, this does look a little bit daft, doesn't it, for RF? And indeed, and this is, the biggest part where it started to be very problematic for RF, because in optics, this particular problem didn't really matter, because we know that light doesn't disperse. And so when you're generating the mode in optics, it's sort of got a source that's still pushing the light to still keep in that direction. Of course, that does mean that in the middle of that light source, if you can think about it like that, it will have a kind of hole in it, because right at the center, they will get out of phase. And so it's almost like you're transmitting down the optical fiber sort of tubes of light, if you can think of it that way, where there's just a very minimal intensity in the middle. But still, it could pick them up. Whereas with RF, yeah, you can just radiate out. And of course, they get lost, and then they also start reflecting off things that in the propagation environment. And that will be problematic because they'll reflect and get to the receiver. They'll start messing the signal up. You can't quite decode it very easily. And so it doesn't work well for long-range communication, because indeed you would have to separate your receiver antenna so far to pick it up. And they've certainly over the years since 2011, yes, there are a lot of research papers out there building antennas and thinking, yes, how many modes can they achieve? And yes, the ones I've typically seen published and ones I've had to review as well for publication have been in the order of maybe 6 antennas, that you could make technically 5 modes with those. And they've had to do things with them like add lenses to them, so that you could try and refract those beams to go back round to the centre, and it would give it a bit more chance to propagate a bit further, and then you don't need such wide antennas at the other end. And also there have been, yes, other clever ways of trying to reflect them well, to make them reflect in the right direction and this sort of thing. So that has been played with. And they're only very useful really for fixed links, not sort of mobile links, because you can't keep moving and follow the mode. So, but they do have potential, and certainly when I was working with Ben originally, he was looking at this because with rail communications, it's not just the link from the track to the train, it's also the fact that you need to, what we call front haul or back haul, the data to those access points, because you haven't necessarily got a fibre to do that. So it would have to go from the fibre cabinet and then go to all the access points down there. And if there isn't enough bandwidth, you want to have all of these modes that it can transmit in a straight direction to get the data to serve all of the users when it comes from the access points. That's what it aims to do. That was when then I could go to Ben and say, well, as well as doing OAM, why don't we try and solve the other problem of trackside to train communication with LAM. And that's where we started to take things a little bit further. So, getting to the point of my title, Unravelling. Obviously we've seen that from the ring, isn't it? They're orientated in that way. You can just cut it somewhere and unravel it. And you could take all of those phases in the first mode that we have here, and we have got it all in a long line. The tunes that I referred to are still being played there. I suppose the other point there is the momentum. Is the momentum still happening? Well, yes, arguably, if that's partly down to the distance you are away from it compared to the length of the bottom line. But yes, ultimately, all of those phases would keep changing. Either you're in a fixed position, they keep changing in time. So there is a kind of momentum moving in that, moving, I say, in that direction. Does it have the same problem as OAM with the phase, anti-phase problem that we have just talked about? Well, if you go a long distance away, yes, it does. Because with OAM, they talk about this as the Lauger-Gauss beams, is what name they get. Whereas with linear angular momentum, I would say that it was more just something that where for those who do antennas will know about broadside radiation and end fire radiation. I would say it's a bit more like end fire, where they are out of phase if you're in this direction, but they will start radiating out there in those two directions. But we don't want to use LAM for long distance anyway, so that kind of doesn't have to matter. And indeed, where I have been looking at LAM, it's more that all of the antennas we would have along this line transmitting these different phases would have the antennas receiving it not very far away, and so in a sense we would be, if you looked at them as two large antennas, we would be very much in what we call their near field of each other. We could more easily encode and decode the modes in that way. It could go to further distances. It depends on how directive the antennas you're using are and what purpose that might serve. There might be a reason for it, but we've been more interested in the shorter range. Of course, it's also possible you can do the other modes in linear form as well, just as we are doing indeed. And that's how they would show up. And of course, if we wanted to go, and it's a bit easier with linear to see the larger number of modes, isn't it? Because when we have 3 modes, we just have 3 of these sets of colours, and 4 would be 4, 5 would be 5, etc. And they would keep increasing. So at this point, it's useful just to see how they look at in research, or look like in research publications. Obviously, I've done these illustrations because I think that's the kind of best way in which to help understand what they're doing in a tutorial form. But these sort of illustrations they show often in papers where this is plotting showing the magnitude, so it's just taking a plane there to show the intensity of the field, and of course at the centre of where the propagation direction is, indeed there is a null there, and it gets very low, whereas it does radiate out in the edges, as we are indeed seeing. And and this one is probably a more confusing one to look at, is then thinking about how the phase pattern looks if you just did take a cross-section like this, where it's a bit of a brain teaser. You would have to look at this and think, okay, when I make that ring bigger or smaller, because of course you could have lots of concentric rings also doing all of those phase sources, and of course as your radius of your ring gets less, obviously the rate of phase change will get quicker, won't it, over the length around the circumference, and it would show something of this spiral effect that we would see. And a lot of the publications that show what the antennas are doing would plot those kind of phase plots to show that there was something there. And of course, by unravelling it to make LAM, which I think is much more logical and easy to understand, yes, if you're near enough to it, you would see a constant magnitude. If you went further away, you would not. You would see nulls, but we assume we don't, and then you would indeed see this linear change in phase as we go along. So, how does all of this modes help multiplexing? That's the sort of next stage, really, to get an understanding of. And we'll look at that in terms of OAM. So I'm going to focus only on when the transmit and receive antennas are quite near to each other, because it's then easy to see that, okay, one transmit antenna goes to one receive antenna element, and what we do if we want to transmit one mode, obviously I've just made all the colours different here to represent the fact that each of those antennas will transmit a different phase, and then of course the receiver ones will have corresponding colours to say that they will receive that with that phase, or the conjugate phase more technically, so that means they all add up. And it means if I set all of the receiver antenna phases to another mode, they wouldn't pick up this transmission. And so that would be all fine. And actually I've done a set of all of the, and I had 6 antennas here, didn't I? Yes, in the ring. So I've created 6 sets of these, where you'll see discreetly that yes, all of the colours have got a slightly different shade. It may not be too obvious when plotted here, but the point is to say, yes, I'm transmitting 6 different modes, and in each of those I'm setting up the corresponding conjugate phase in each of those modes to pick up those modes. And another important point there is that you see 6 pairs of antennas there, but actually we can do that with just 6 and 6 transmit and receive, such that you would connect all of those 6 modes to the same set of transmit elements, and you would be able to decode or demultiplex those 6 modes at the other end, and you'd be able to do all of that at the same frequency. So effectively you could transmit data down all of those different modes. They would not interfere with each other. We're effectively giving ourselves theoretically an opportunity to transmit 6 times more data than we could if we only had one mode. And that's how we start to get to the phenomena that we often call in communications of spectral efficiency, making better use and better transmission of data over a limited spectrum. And that is indeed what they're trying to do with OAM for fixed links, that they can make better use of the limited spectrum they've got, and very easily transmit these modes. And the nice thing about it is that the maths that shows the phase that you need to have in each of those modes is actually very simple maths. You just increase the gradient each time to change the phase. And it's very straightforward. We don't have to do what communication systems do with multiple antennas, is trying to work out the link and what the conditions are, and then start to do heavy computation to find the phases, which is done in what we call multiple input, multiple output systems in communications, which do utilize multiple antennas at the transmitter and receiver. And so it's a very effective thing to have, and indeed that's very nice for optical communications, because it's got a very straightforward way of working out how to encode and decode its multiple streams of light that it will send down the fiber. But of course we have that problem with when we do it with radio, it doesn't work for long distance. But taking OAM a little bit further, which this is more relevant to radio than it is to optics. Now I'm sorry that we did discover that my animated GIF that I have in this doesn't actually work on here, but I think with the arrow you can probably quite easily get the picture of what would go on, is that I set it such that this receiver ring would just rotate. So of course the yellow would go to green, the green would go to blue, etc. And then they would keep radiating. Not radiating, rotating as it goes around. And of course I'm only transmitting one mode here and receiving one mode. Now the interesting thing is you can rotate that OAM to any of the 6 positions that you effectively can get there. And actually it doesn't matter if you do that. You can still decode all of the modes. It is theoretically possible. And of course with a fixed link with OAM, that just seems silly. Why would you rotate one of the antennas? You can keep it fixed and it still works. But when we unravel it for LAM, that provides a very interesting opportunity. And that is where, again, this is an animated GIF, but of course we can think that, yes, we have unraveled the receive ring. What we've done is unravel the transmit ring, but then taken other rings and added more. So of course it has the 6 colours, it repeats the 6 colours here, keeps going along for the tunnel edge, or the track side we could call this, and this would be the train, because obviously the train carriage has a certain length. So this one would go a certain number of antennas. And what the GIF would have shown is that this train would have been moving along, and obviously the colours would overlap differently, but still that one mode could transmit and be received as the train moves along. I sort of call that, wraparound, is that it just keeps circulating and then gets back to until all of the colours match again. It's wrapped around. And of course I can still transmit the other 6 modes doing this. Obviously I haven't shown those for clarity, but we still can multiplex those 6 modes quite happily. And they're all fixed phases and everything. And of course this train would be shooting along at high speed. And of course those who know physics will know the phenomena of Doppler shift, where it will offset the frequency a little bit. That's quite problematic in wireless communications. But usually when you're looking at something going straight past, like so, then that Doppler shift is near 0. And so this is doing a nice thing. We're sort of making the wireless link as short as possible, having the trackside to train, or indeed the top of the tunnel to the top of the train roof, which is about the most practical place to put it, which would be probably this sort of distance if we're talking about the tube in London, particularly on the very vintage designs of the tube. And it's effectively almost doing as much as you can before you actually have to connect it physically, and you don't want someone running behind it with the fibre going along, so that's not going to be practical. But of course, like OAM, designing good antennas for LAM has its challenges. Like for example, what happens when your train antennas are in between, where the antennas here are sort of at this point, so they're not quite, they're in between 2 antennas here. There's kind of there's clearly an overlap point, isn't there? And how do you make that connection seamless so that it doesn't affect the communication? And that's getting quite interesting, where we're now working on new antennas and designing antennas in quite a different way to the way we've designed them before. Because the way we design antennas normally is either to make them very directive, to radiate in a certain direction, to be very omnidirectional, that they don't know where the transmitter's coming from and they can pick it up, or they could be sort of semi-directional, halfway house between the two. But actually, this is something very different. This is about having a sort of constant flux. So when you see the train going past, you almost want to be just seeing a kind of linear what we call is a constant flux transverse to the direction of propagation. No, sorry, let me get that right, because I'm confusing it with the lecture I was giving earlier at the university. It's where you want to get a constant flux transverse to the direction of travel. Yes, because the direction of travel is that way, and the flux all the way along that transverse, which is orthogonal, perpendicular, needs to be constant. Yes, and so that's really, really important. And I'll come later to how we've started designing antennas to fulfill that purpose with very recent measurements we even did a couple of weeks ago. So you get interesting, fresh information there. But we will now have, well, we'll now sort of get to the sort of, I suppose, the application. Of course, I said really earlier that, you know, the problem with getting connectivity to trains is partly due to the technology available, but partly due to economy. Yeah, outside of a tunnel, connection is not so much a technology issue. It's the fact that you would need to go putting masts every 1 or 2 kilometres down the track, and assuming the track's very straight, you could indeed have quite a good directional antenna, which would go towards the train as it's passing, and it almost just has to tilt a little bit to the left, and it will follow it. And it will make the connection happen, and then when it gets too far, it can go to the next access point and carry on. And the radios that they're using for these kind of things, there are indeed industries doing that. Indeed, we had at IET Surrey a couple of years ago, or 2 or 3 years ago, EvoRail come to speak on how they trialled all of this on the Isle of Wight island line. Very interesting lecture it was. And indeed, they're doing very interesting technology there at the moment. And doing it in a sustainable way as well, actually having wind and solar power to power each access point so that it can readily get communication to the train, and then of course that would mean that's acting to supply to the train, and then that will have to have its own wireless or Wi-Fi or small cell network within the train itself to then serve the users. And indeed, that is a way we definitely do need to go with trains in the future, and I would certainly refer to books like the former president of IET, William Webb, who wrote an interesting book recently, The End of Telecommunications History, where indeed he does argue coverage is actually the problem we need to solve, and I totally agree with him. And he pointed out in his book, which I was very pleased to see, that indeed we do need to be getting access points into trains and make it work well. But of course it's costly to do that. And indeed in tunnels, there aren't effective ways to do it at the moment. There's only 3 ways you can really do it. And the way that the Tube in London is doing it right now, because some of you might have noticed that they're now delivering 4G and maybe even 5G in some cases, services on the Central Line and the Jubilee Line, and I think some of the Victoria Line and Northern Line. But I did a few weeks ago go and take one of those so-called smartphones. I don't own one, I don't believe in them. But I went to try out how good it was, because they use the technology known as leaky feeders, where you literally, well, apparently they have, so according to the person interviewing the TFL on YouTube, a very thick coaxial cable, or probably a set of them I would imagine, and you just go and cut holes in the cable and it leaks. And so it will then, that's put probably along the side of the tunnel, I would expect, so that would then penetrate through the windows to where the users are. And leaky feeders are, yes, they're very economical, well known, but the difficulty is that you need an awful lot of power when you're sending the downlink, i.e. the signal from the tunnel to the user, because it will attenuate quite a lot as it goes down that tunnel. But the real problem is, and this is where I found they failed abysmally, it was okay for downloading videos and data. It did do that quite well actually, and it seemed to work with WhatsApp messages. I haven't quite worked out if it did work or not, but I'm not a fan of WhatsApp, but I could see that it could do error correction going up, that it would probably work. But the one thing it definitely failed on, I repeatedly, was dialing the number of my office phone and trying to phone it up, and hopefully not get one to answer it. It failed on every occasion. And not until the time we actually came out of the tunnel on the Jubilee Line to where it's above ground. And I thought after this, well, It's obvious why it didn't work, because those who know RF will know that you do not want to have a receiver where you've got a long feeder cable behind it, because the noise that will generate will be colossal. And of course the power that can only come out of these phones is 23 dBm or 200 milliwatts. It's not going to go up those leaky feeders and get there. And yet I was really quite shocked to find that TfL are saying on their website that you can phone up on the train if you want to. It didn't seem to work for me, and I don't think it will happen any time soon. But yes, watching, from what I could tell, videos on YouTube seemed to be possible. That was one possibility, but it's not solving the problem entirely. And then the other solution is you could have distributed antennas, which certainly Berlin, from what I have seen, are doing on their U-Bahn, and they've actually got usually not so many vintage tunnels like we have. I think they're usually quite a bit bigger, so they had a bit more headroom to what they say is strategically put the antennas in the right place so that it delivers the service well. But I've seen some vloggers not too happy about how it's working, so that will have had its problems. And of course you get lots of multipath, lots of reflections in the tunnel, reverberation. That will mess up your signal. And you're still using common communication modulation techniques like those who know communications know orthogonal frequency division multiplexing, and that kind of channel is not good for OFDM. It will mess it up. We really do need to rethink the antennas and indeed the radio system as to how we transmit it. I suppose the other third option we've argued is free space optics, where it uses lights that you can't quite see, but you can propagate data down it as a kind of light link, but you need a very straight line, and dust in tunnels and things like that would really muck it up. So it's not good for that. So really we do need a better low cost, low energy alternative that would actually deliver the spectral efficiency we need to serve the thousands of users, of course, that we have on board our trains. And of course, what about hyperloops? You know, we ran an IET Surrey lecture, well, just a bit after coronavirus, and we decided to do it online because we were able to get speakers to come and join together from Europe to bring that together. Actually, it was a really interesting lecture. You know, these things are actually not that far away. It's 10 years away. On very flat lands, sort of Dubai area, I believe, UAE, that sort of area, these things could become true. And actually they are interesting alternatives to things like HS2. They don't take up as much space as they look. And of course, when you're stuck in a tube like that, cellular communication isn't going to solve things, and we do need something that works. And people will want connectivity on a Hyperloop, however short the journey might be. Although they do have a lot of problems, they were saying, with the fact that they accelerate so fast and it takes quite a long time for them to decelerate. So that will be another problem that comes about. But anyway, I'll tell you a little bit how I came to start doing LAMM. If everyone's watched that film, The Theory of Everything, the story of Stephen Hawking, and that moment he was trying to put his jumper on and he saw the fire and he saw something through his knitted jumper, didn't he? And he thought, that's a new idea. And he came up with something for theoretical physics, and I thought, well, you know, I had one of those moments. Near to where I live in Guildford, there's this very nice little road that I walk down to go into town and come back from town from them. And I was thinking about when we want to get connectivity to trains, we need the shortest link possible. Right, how would we do it? And I was looking down at this little brick road, and I was looking at these bricks, and I thought, yes, multiple antennas along the track. Use the rail sleepers. Let's communicate under the train, I was thinking at this time. Not that it's actually practical to do that, but for a lot of reasons. But I thought, what is the way to encode this? And that took me on my journey, and I thought, well, actually, LAMM is probably, this is what we need to unravel OAM and LAMM. And I went to Ben and I talked to him about it, and I said, hey, should we try this? And we thought, let's go for it. And that's how it began. Of course, in a tunnel scenario, because I thought at first, under the train, you don't have to put masts up, it's very easy to implement, but because you have to do engineering works on railway tracks a lot and pull them up and take them down again, wouldn't have worked. And of course there was the argument that, well, you can put masts up anyway for outside the tunnel, so what about in the tunnel? We need something alternate, and this was where we did identify that the technology has potential. Of course, to get the kind of seamless connectivity, we need to have a way of putting a strip of antennas that are very easy to implement and low cost along the train carriage, and have small radios put there as well, and whatever, and then have fixed antennas along the top. This would be the kind of setup it would have. But you don't necessarily have to do just one strip. We've actually been more thinking about this in what we would term 3D angular momentum, where we could indeed have two strips, for example. So we're actually thinking along that dimension as well as down it, to say how could we get more strips of data or streams of data through down these different antenna strips. And we could indeed do a hybrid of those two, because in the first one that would be more that you'd have one of those antenna elements essentially being one length, and then the next one and the other, and then of course when you've got them in series like that, of course you have got the sort of overlap point as well when it crosses from one antenna to the next. Yes, we have to accommodate that, but that's actually down to how we would design the radio, because you know when those trips are going to happen, you could start setting up your modulation and coding to follow that. That's how indeed it could work. Yeah, so we can, and we've had a go at building sort of antennas like these, where we've taken commonly known patch antennas, because we want a nice flat antenna. Patch antennas are great for that. Could we put them very close together, and could we start experimenting with them when you do have one on top to see, what is the connection looking like? And indeed, a student was really helping me last year produce these, which was really good, and we've extended it to make 16 elements, because I could get some more meaningful results doing that. And we literally have a platform, much like one that's used for a milling machine, that we can turn it to position it along linearly, and we've got it in our anechoic chamber here, where I've got a little patch antenna on top here. So that's like the tunnel top, and then there's a little gap of about 10 centimeters or whatever, and we've got all of our strip antennas along here, so we can see how is that flux looking as we move along. Is the channel staying constant along there? And indeed, we put some polystyrene here deliberately because I didn't want to get any multipath affecting the measurement. So we had to set it up taking consideration of that. And I'm getting something so far where the magnitude is fairly flat. I only did these measurements actually about a week ago, still processing them properly, but the phase also should be very constant as well, because indeed when you want to do all that multiplexing, you need along that link the phase of the actual physical phase between the transmitter and receiver to stay constant, so that indeed you can start multiplexing all the phases you want and get the output you want. But partly the reason for that, the phase not looking quite so good at this stage going back, is because I've had to make two small antennas, because usually when we print onto PCB we can normally only print something as big as an A4 sheet of paper. So I've had to print two of them and stick them together, but I've got another student this year where we're going to look at trying to do that a bit better. So then we only have to have one feed from the centre, it will distribute out to all of them, we'll hopefully get the phase looking a bit better. So it's still very much a work in progress at this time, that we hopefully can get to a point where we can later this year submit to publish the first paper on a seamless connectivity antenna that would be useful for something like LAM. And it would be great if such research would start getting interest around the world. And we've had lots of people doing publications on OAM antennas. Wouldn't it be great if lots of people did publications on LAM antennas? And that would be fantastic. It would be groundbreaking to see that happen. Indeed, we would be doing further work on what would be practical. These are built on sort of FR4, which is quite solid. That's not so practical to put on a railway train, but we could start using flexible PCBs and things like that. Actually, literally, they could roll out and stick down. How would be the best way to do that? There's an awful lot of work to do yet in making those antennas work, and we need to influence the research community to do it, because there's more work to be done than we can do. And indeed, we need to do propagation measurements in environments, not on real trains, because that's far too dangerous, but we start with things like garden railways. Guildford Model Engineering Society, where we've done some measurements last summer. We'll hopefully get to do some more this summer as well. Literally just building a model tunnel, not having a tunnel, seeing what the multipath in the tunnel does. Does it affect it? Hopefully not, because you've got quite a strong line of sight link, and then not much reflection could be that significant. And we've been plotting some curves there where, yes, I've been looking at the phase that you get across these two antennas out of the tunnel where it's quite flat. It gets a bit less flat when it's in the tunnel. Yes, we are seeing things not quite working. We need to get some better preliminary results on there. Anyway, yes, I don't often do slides with a lot of text on, but this is hopefully going to conclude things. Where next? Obviously, we are needing to do proof of concepts, as I've shown, on garden railways, yes, using software-defined radios as well to help show the data throughput they can achieve, this kind of thing. We also need to go working with heritage railways. How could we then start to get proper models of bigger tunnels and what the propagation would be like there? And we can't measure that at high speed, so we often need to do a measurement at slow speed or very little speed, and then take that data, and then you can, in post-processing, speed it up so that we could then emulate it as it was going fast, see what's going on. And we need to go beyond, at the moment we've only been looking at 2x2 cases where you've got 2 modes. We need to probably go up towards 10 modes to start to get the 2 to 3 gigabits per second connectivity that is likely to be needed for train connectivity based upon the data demand that exists. We have to see that all get demonstrated in the years to come. So that pretty much, hopefully, is about, I took just 5 minutes over what I should have done, but I hope you'll forgive me for that. And, well, actually, no, I didn't, because there was the intro from Mike, so I did take an hour, yes. So I am all right. I hope that was straightforward and informative. And I guess, yes, time for a few questions.
Questions?
Okay, so you say it's for a short length communication. So, and if it's short wave, what is the minimum distance you must not go beyond before you start increasing the size of the receiver?
It's a good question. It's not one I've yet explored.
Is it also longer distance or shorter distance as you increase the mode number?
Yeah, with more modes, yes, the distance would become, yes, it would matter, you're right, because, yeah, it's as soon as you start, because the distance, I have never formed it yet to know exactly, but I know another paper is needed probably to define this properly, but I would see it as, it depends how far spaced apart your antennas are, and then the distance that you do relative to that spacing. If you go too far relative to that, then you will start to find that the phases start to cancel out, and you don't see a constant magnitude anymore. And so it would need a kind of sort of synthetic experimentation there to see, yes, where does it fail. I mean, usually the distances we are dealing with have never been anywhere near that anyway, so we've not usually worried about it. But it also would depend a bit on the directivity of your elements as well, because you could have very directive elements one way, so that then the antiphases wouldn't interfere so much with the in-phases. So there are things we could do to extend that by virtue of the antennas we design. And yes, as you increase the number of modes, obviously the phases are changing more quickly, so the sensitivity to that would grow. And of course this is one of the challenges with how many modes you can achieve, because as you go up in modes, the sort of the phase difference between modes starts to get more small, and so phase uncertainties, phase impairments in your RF could be quite then big compared to those differences, and then the modes start to get messed up. So there's absolutely going to be a fundamental limit, or practical limit I should say, on the modes that we're going to ever be able to generate. And this is indeed more to learn in practice. With genuine RF impairments and things to what we can actually get to. And indeed we're hoping to get some more serious research projects behind this that would actually really go and deal with the nitty-gritty science below this. We've only got the seminal conceptual idea at the moment to show, yes, it's got a chance. Yeah.
One other question, if I may.
Go ahead.
Let's take the first mode. Why does it, you need a bigger antenna in order to capture all the energy that's being transmitted by the transmitter antenna?
Oh, you're talking about OAM here?
Yeah.
Yeah.
Why does it diverge? I don't know if it's the right question.
Yeah, the divergence is the word we use when indeed, because as I said, it was the fact that when you're looking straight ahead, you've always got a phase and an antiphase countering each other. So it's when you look at another angle, it's like the path difference starts to change at that point. So that antiphase can't happen, basically. Yeah. And so, yeah, where it actually sends anything is out there. Yes.
Are there limits on the frequency ranges that you can use for
Yeah.
a remote, given practical antennas?
Indeed, and in the seminal paper we did put this in. Yeah, anything above a gigahertz basically is really what's realistic. Because the distances we're dealing with, if you go below that, the sort of near field starts to become too close, and it's more like coupling than propagation. But that's a good thing, because actually it's anything above that that we would ever want to use for it. And indeed, that's a nice thing as well, because when we talk about tunnels, it's not so much, spectrum licensing that dictates what frequency we can use. It's what is a practical radio to use, and indeed I've been focusing on S-band 2 to 3 gigahertz range, because that's always a lovely frequency for an RF engineer to play with, because you haven't got the problems of low frequencies and you haven't got the problems of high frequencies, which are unique in themselves. But yes, eventually, it may be that they say, oh yeah, you need to use millimeter wave, I'm going to have to go up there. But I don't see a lot of point in it, because the cost of the radio would be so much more. And indeed, when you've got the spectrum available, why not use it? But obviously Ofcom may have another view on that. Yes.
Hi. For the particular measurements that you've done, for a given number of modes, what sort of bits per hertz are you likely to get?
Well, that's down to the SNR you can get. Now, that's another nice thing about it. Of course, the propagation link's so short, so you don't need to transmit a lot of power. And it's quite hard, it's ironically quite hard to get a low SNR, which makes it interesting. Yeah, and I think certainly with practical cases we've been looking at, it's quite hard to get anything less than 30 or 40 dB SNR, and that's already pretty good. Even, with just one link, you're going to get quite a lot of data throughput there, because yes, the data throughput you can get will always depend on your signal to noise ratio, as well as your bandwidth.
And the number of modes, I guess, so each...
Yeah. Yeah, and that's it. And I think we took a practical SNR with 10 modes or whatever, yes, and that would deliver within 20 megahertz of bandwidth, we would get the order of data throughput that we need.
What was the throughput for 20 megs?
Yeah, because the first paper we did, which we presented at the conference paper at the 5G World Forum, we decided that for that it could go up towards with 8 or 10 modes, I think it was. Yes, we'd get that but yeah, you have to make assumptions about the SNR you're getting, which would be 30 or 40 dB probably. Then yeah, it would happily deliver. I mean, of course, we'd have to still prove that with demonstrator radios and whatever, because the RF impairments and other things will come into the equation. But yeah, by theory, that is what we should be able to do. And it's just like any MIMO system. If you can create many orthogonal modes of communication, you can up your game.
I didn't get what the... So for a 20 meg channel, in your measurements for the number of modes you operated, what throughput did you get?
Oh, well, we haven't measured that yet. We haven't proven it. We've only looked at it theoretically. Yes. So this is it. This is where we're doing sort of 2x2 at the moment, and we need to sort of use lots of SDRs to try and get 10 modes. And yes, in theory, that should deliver us 2 to 3 gigabits per second. We're just trying to we're obviously keen to get to a point where we can show that's happening. Yes, and indeed at high speed as well, because you could emulate the high speed and show it. Yeah.
Just a comment, SNR for the non-expert.
Oh yes, sorry.
SNR means signal to noise ratio, and it's an obvious figure of merit. Okay?
Yeah.
Further questions here?
When do you think you might see this rolled out?
Well, of course, we're doing the science, and it has to be at least 10 years ahead. Yeah, and of course, it's down to, yes, if we get a nice bit of taxpayers' money, which I'm hoping to get to pay for a nice project, which will get some researchers. We will see if I am fortunate enough or not. And then, you know, because yeah, it's the technology readiness level we have to get it to. It's up to 3. It's more like 1 and 2 at the moment. It needs a demonstrator to show it's at level 3, and then you know, getting to level 4 and 5 would be sort of testing it more in situ. That would be, yes, okay, the industry coming along and saying, oh wow, this is a good idea. Let's take this on and help, and let's try this out in a trial tunnel and see if it actually does go to a train and does it. That would be a starter point, and then of course it can get towards commercial possibilities. But of course, it will take a lot of movement in the rail industry to make this kind of thing possible. It's going to be needed, because I say, you know, as we see in the London Underground, what they're doing at the moment is it's much easier for them to just go and put a few leaky feeders along there, because they don't have to worry about putting any infrastructure on their rolling stock in order to get connectivity to their users. They'd far rather just penetrate through the windows, silly though that is, but it's a solution, and it's giving something better for their customers. Yeah, but it'll last a while, and probably the customers will overuse it one day, which we shall see.
Are there any particular post-processing challenges behind the receiver antenna once you have received multimode?
Yeah, well, this is exactly the point of using OAM and LAM, is that all of your phases are fixed. Because with other multiple antenna systems, yes, it would, well, you know, with a base station, for example, that has multiple antennas, the mobile will send a pilot channel up to it, to all of its antennas, and say, right, what's the channel state, as it's called, and it would have to work out all the phases it needs in order to get a beam down to me, and in order to suppress all of the interferers around me. And of course it can't do this when a train is zooming past. It hasn't got time to do it. So this is the whole point. You know what the phases are before the train gets there, and it's simple. And it will make the radios incredibly cheaper. Yeah, that's the benefit. And we don't need to well, the only thing we have to worry about then is to sort of know where the train's going and then switch the next radio on to pick it up as it goes. Because yeah, all of the data will come down telephone lines from their baseband. It won't be at RF. The RF will all happen in that box there. Yes.
I have a question, Tim. The London Underground, I was up there a few days ago, and there was a station that advertised good Wi-Fi, well, on that line, but how true was that? I didn't bother to try it, and would not that, whatever scheme they're using, compete with what you got? And would it be true to say that you could promise bigger bandwidth or faster if these methods come along? So multiple questions.
Yeah, definitely, and of course the Wi-Fi that's delivered will be limited in what backhaul it has, because the thing that Wi-Fi still has to do is get a link which will have a limited bandwidth or whatever going to that access point, and then it would have to deliver it. And I think actually a good point there is the best place to go to sort of see in numbers how far off it is to go to South Korea, and I looked on YouTube to see what they're delivering, because of course in Korea they are delivering as high data rate as they possibly can, and within the stations in their underground lines they have I think I remember it was 384 gigabits per second to distribute between all the users in the station. Whereas within the tunnel, they only had 70. So that's how good they've been able to get it, and they'll try the best thing they've got. So you know, that's kind of the sort of thing to beat. And yes, yeah.
How is South Korea doing it in tunnel?
How is
South Korea doing it in tunnel now?
I don't honestly know. I would expect they've got more probably. I think actually, yeah, no, I think they've got distributed antennas, because I've seen some of their research publications certainly talking about distributed antennas, yes, and that's how they've done it, because there's more of a preference often with higher data rate connectivity, because the argument against leaky feeders is if it fails at some point due to overheating fire or something like that, it cuts the whole lot off. And it's quite hard to re-repair, so they'd rather distribute them, so if one goes wrong they can still have the others. Yes.
Anybody else? Okay, well, it's my task to thank you very much, Tim, for coming along and giving us a good picture. I must say, from my own point of view, I knew Tim was working on this, but I didn't have any idea of how far it had advanced. I looked at one of his early papers, and it's advanced a lot. That I think what we've seen today is some real leading edge, if not bleeding edge research directed towards a real practical problem, which is basically getting better Wi-Fi, if you like, on trains, whether above ground or below ground or in tunnels. So I think, could we show some appreciation in a minute? But before we do that, allow me to present from the IT, first of all, a certificate, which is to prove to your wife, Rebecca, that you were actually here. And the second thing is, this looks innocuous, but this is a very practical IT thing. It's a card which you put amongst your credit cards, and it stops people with a reader as you walk by, actually triggering off your, or getting your codes off your card. So that
Lovely.
is that.
Thank you.
There's also an IET pen, which I use to sign your certificate.
And it's got the latest logo. Thank you.
So I think we should all show our appreciation for a very, very interesting thing.
Thank you. Thanks so much.